For a two-object system, the center of mass is always closer to the heavier object. Consider a large mass, capital M1, and a small mass, lowercase m2. Let big M1 be located at a distance x1 from the center of mass, and let little m2 be located at a distance x2 from the center of mass. Okay, so the distance x1 and x2. These masses and lengths are related by the equation m times x equals m2 times x. The motion of a system's center of mass. The center of mass can move and even have its own motion change. If any object of a system is moving, then the object's center of mass can itself be moving. The velocity of a system's center of mass is determined by the total momentum of the system. The momentum of a single object is momentum equals mass times velocity, remember? Velocity of a system's center of mass can be found using the equation the net system momentum equals the total system mass times the velocity of the system's center of mass. Alright, so the red car is twice as massive and is moving to the right at 4 meters per second. Finding the center of mass velocity using momentum principles. Before the collision, the momentum of the system is the blue car is 1 kilogram times 6 meters per second to the right, plus 2 kilograms, the mass of the red car, which is at rest, equals 6 kilograms times meters per second. Use this to find the center of mass velocity. The net momentum, which was 6, equals the total mass times the center of mass velocity. Here you can see you divide out 3 from each side and you're going to get the velocity of the center of mass, 2 meters per second. Did you notice the center of mass velocity does not change even during or after the cart's collision? This is because momentum is conserved during the collision. Conserved momentum means the net momentum is constant. Since net momentum stays the same before, during, and after the collision, the velocity of the center of mass also stays the same. Is it possible to then change the motion of the system's center of mass? Yes, but only with an unbalanced external force acting on one or more of the system's objects. If an unbalanced external force acts on any object in the system, the center of mass will accelerate according to Newton's second law. The net force equals the total system mass times the acceleration of the center of mass. Consider all the forces acting on the carts as they collide. The red cart's weight is balanced by its normal force, balanced external forces. The blue cart's weight is balanced by its normal force, balanced external forces. The blue cart pushes the red cart, and the red cart pushes the blue cart, an action-reaction pair, which is an internal force. There are no unbalanced external forces. So the center of mass cannot change its motion. It's always going to go to the right forever. In the real world, there's going to be friction that will slow down the red cart and eventually bring the red cart to rest. And if that's happening, that's an external force that is unbalanced on the system. So you're going to see the center of mass begin to accelerate down to 0 when both carts are at rest. Now look at this situation where the carts are connected by a spring and a constant green force acts on the red cart. The pink arrow represents the internal spring force on both carts. Notice that the internal spring force is equal in magnitude but opposite direction for each cart, making the spring an action-reaction pair. When the spring force is high, the blue cart has a high rightward acceleration because the spring force is external to the blue cart. When the spring force is high, the red cart has a low rightward acceleration because the spring force partially cancels the green force and both forces are external to the red cart. There it goes. But if you look at as a system, the spring force is internal to the red-blue system. That means the spring force cannot affect the acceleration of the system's center of mass. The green applied force is then external to the red-blue system. This means that the applied force is part of the net force that accelerates the system's center of mass. The net external force is a constant 2.4 newtons. The total mass of the system is a constant 3 kilograms. Therefore, according to Newton's second law, the acceleration of the center of mass is 0.8 meters per second squared. So even as the spring makes the carts wiggle, the external mass has a constant acceleration due to the constant applied external force. The end. If this seemed confusing to you, go back, rewatch, know when to identify external forces versus internal forces, and know that the center of mass for a system has a velocity, and that velocity is not going to change unless there's an external force acting on the system.